Welcome to the section Stream Processing with Apache Flink Transformations. Data Sources. In this video, we will look at Flink data streams in general and then look at the data sources, how we can get the data in. We will look at socket-based streaming, file-based streaming, and Kafka-based streaming. Flink data streams. Let us first try to understand what data streams are all about. If you look at the picture, you see that there are many messaging systems out there, such as Kafka, Amazon Web Services Kinesis, Azure IoT Hub, and so on and so forth. In all such systems, the typical application looks as in the diagram. There's a producer always, which is putting events onto the messaging system, or the message bus as some might call it. Then there is a consumer or more consumers which are consuming the events from the messaging system. So imagine Uber, imagine weather sensors, imagine other types of sensors which are continuously sending data to your centralized system. There must be some kind of a consumer which is consuming. That's the whole point of why we are looking at Apache Flink for stream processing. So if you look at this picture carefully, you see that there is a continuous stream of events that is coming in and the consumers are consuming it. If you see this, the first event is consumed, we turned it to green, the rest are still yellow. So the consumer continuously consumes, which is processing all the events as and when it receives it. This is the basic principle behind any messaging system or message processing system or stream processing system or real-time processing system, real-time analytics. There are many different names, but that's the underlying principle. And now we will look at what are the different things that Flink can do. In Flink, if you put the consumer in Flink, there are many things that need to happen for it to be reliable and then process everything. So we will look at that from that perspective. The first thing we want to understand is the parallelism concept. The parallelism is of two types. One is data, the other one is task. Flink can take the incoming data and partition the data across multiple machines in order to scale up the processing. The other way is to do task parallelism, where typically nowadays people have multiple CPUs anyway on multiple systems, because if you buy a Dell blade with 48 cores, you don't want to just use one core, right? So you can have many cores, and in some use cases you could use multiple CPUs to do multiple tasks at the same time. Right, so it's not like one thing fits all, data parallelism versus task parallelism. It depends on your exact application. You should be able to determine which one you would prefer more. We'll look at this further in all the coding examples, how we do different things. The Flink data streams offer the following advantages. The first one is called exactly once processing. If you are processing a real-time system, because of the nature of the distributed systems which are serving as the message buses as well as the processing, many times you will see that the event is either processed one time or more times. It's called at least once, or sometimes the event might not even show up and you completely missed out, which is at most once. So you don't want to have may or may not process, or I will process it multiple times. Either way, it is not a good idea. Exactly once means you are processing each event exactly once. If you go to a restaurant and order a Coke, you want exactly once. You don't want them to not give you a Coke. You don't want them to give you two Cokes. You just want one Coke, right? So hope that makes sense. The second one is called state management, because many of the streaming applications, let's say Uber, you booked a ride on Uber, you have a state management. You need to be able to track it continuously so that you know exactly what's going on. So Flink offers that very well. It's called state management. The third one is handling of out-of-order data. That's a huge thing. If you look at other systems such as Apache Spark, only recently Spark is able to compete at this level with Flink in terms of how well it does out-of-order data when it deals with real-time streams. Flink has been doing it from the get-go. The handling of out-of-order data is important because not everything comes in exactly the same sequence. Let's say the time series, or if you look at timestamps, you would like to have out-of-order processing capabilities such that when you receive the data, you should be able to actually handle it the way it is supposed to be. So that's a very, very key point. We will see this in hands-on coding. All these things, we're going to see them throughout this and the next section. The fourth one is flexible windowing. It's kind of window concept. Again, we will cover this in hands-on exercises, but the way to understand window is when you look at real time, it is pretty much an infinite, unbounded stream of events. So you might want to look at typically in terms of window T, which T is in seconds or milliseconds, but you typically look at a window. You don't look at the entire thing because the entire thing has no concept of beginning or end. It just goes on 24/7, 365 days a year, forever. So you need to create a window for which you want to measure something, like stock prices in the last 15 minutes. How many cars are going through a toll booth in last 30 minutes or 1 hour or one day? It cannot be like how many cars, right? So what would you do with that? So that's the reason windowing is again a key concept which is built into Flink from the get-go. We will see again all these things in very nice examples. Checkpointing makes sure that the state is maintained very well. Any problems that you have with the entire system, like you shut down the system or something else happened, the Flink system will be able to recover from many, many errors like that. Again, checkpointing is also something we'll look at it hands-on. The next important concept I want to go through is called the shuffling or data exchange. There are many different types of data exchanges that happen because we are dealing with multiple machines and multiple tasks, and there's a stream of events coming in nonstop. There are 4 different ways that you can look at. We'll look at them in a very simple diagrams, so we'll not spend too much time on this slide. We will cover all these 4 in the next 4 slides. Let's look at the first one, forward or one-to-one. So a task is processing. If you see the green, yellow, and red, task is processing it. Then there's another task. It will receive the same thing in the same order. That's it. It's just one-to-one. There's another machine which is receiving more events. Machine 2 is again one-to-one. So both are simply one-to-one. So these 2 machines are actually processing everything in parallel. Let's say they're consuming from Kafka or something else. This is what's happening, but it's all one-to-one. So there's nothing going on between the machines, no communication whatsoever. The second thing is called broadcast. Due to some reason, in some use cases, you might want to send all the data to all the machines. That's what this is happening here. You might want to see both. Let's say these machines are looking at completely different types on coding. All these things, both tasks need both information. Like you need the blue as well as the green. So green comes from this stream. Blue comes from the second stream, but since you're broadcasting it, both tasks have access to all 6 events. So this has its own use cases, so it depends. If you need to share the data among the systems from 2 different streams, for example, this is what you would do. Hash key is the third one, where you redistribute the data of the streams according to some kind of a hash key or a key based on something from the event itself. So you can redistribute the events and do a nice little scaling or distributed processing. You're just guaranteeing that using hash key you guarantee that everything that belongs to a specific hash key, such as let's say the state in the US, California, New York, or Rhode Island, or Connecticut, they all go to the same task. So it's a very nice way of partitioning or shuffling the data. The fourth one is called rebalance, which is pretty much random because you just say, okay, I want to rebalance it because you don't know what's really going on. You're getting a bunch of events and then you say rebalance. So that kind of does a random repartitioning such that every machine has similar number of events, but there's no real guarantee of anything really. That's why it's called just rebalance or random. Anything can happen, but you're just trying to scale up the processing system. That's the intent here. Now that we have seen this, we're going to quickly look at the 3 types of getting the data in. The first one is called socket-based streaming, where we will look at how to simply connect through a socket and just get some words. And our intent here is to simply get a word count. Don't look at flat map too much right now because we have next videos where we'll cover the transformations. But right now we just need to know that how this code works. So we're going to look at that now. So this is what's going to happen. We're going to paste the code. The code has been provided. Here we are starting a shell. Shell has started. Once you open the shell, as always, we also need to have an NC. NC is a simple application that you can install on any Linux machine or even inside a Docker container which has Linux. So it's simply NC, that's it. If you want to install it, you install using yum or whatever. So anything else you can think of. So there will be a small help file that will be provided in the course, so which will show you how you can install it. But the typically what happens is you just say nzl and then 9000, it starts a server on port 9000. Later on we'll look at having two different servers. That's why we have 9001. We can keep it started, but 9000 is what we are going to use. The next step we will have is to take the code provided as part of the coding, and then we're going to paste that code here by simply pasting it. Okay, so here I'll simply explain to you. So there's a case class word with count, which says word and the count. So we're just trying to count the number of occurrences of each word. So as the server, this is connected to the server socket stream on 9000, you're going to type in some words. That words will come in as real-time stream, and this is going to continuously count it. So we'll see this in action, and then we can talk more about it. So right now it's listening, right? So we can go into this section. We can say hello. Right, there you go. So it keeps printing every second for 5 seconds, and then it forgets that, because as I said, this is like a simple window. We have many different types of window, but what happens is that if you type this, you will understand A, B, 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 right? And then we're going to put another thing called C. Let's see what happens with C. Again, same thing. See, you see that there's a window. So you don't say hello again because the window keeps going forward in time. You don't see everything all the time. If you really want to do that, then what we will have to do is to change this time window, seconds, and this is just update, but time seconds, you can change it to 60 for 1 minute, or you can change it to minutes, so you can change it to a long period of time. So there are many different possibilities how you can do this, but typically what this code will do is keep doing this window based counting. That's all there is to it. Okay, so this we have seen. File-based streaming, actually the code is very similar. There's not much difference except how you're getting the stream here. Here you're getting the stream using read file stream, streaming1.log. There's a file that you maintain, and then you're just streaming from that file. This file could be a big file. Maybe you collected it over a period of months, but you're simply reading from that as a stream. So let's look at it again. This is the socket stream, right? Socket text stream. The second one is called read file stream. That's the only difference really. So if you execute it, it looks like this. Again, it performs similar things if you have a file. So there's no difference really in how this is handled. So we'll execute this code also right now. We'll start a new shell, and we're going to paste this code. This is going to get from streaming1.log. Okay, and that's the end of the file. So let's see what that file was really. Work data streaming1.log. So this was the file. So it just streamed the file and it applied the aggregation and the window function on top, and that's pretty much it. The third example we will see is Kafka based streaming. This is a little more involved. You need a couple of jars, 5 jars really, and then when you start the shell, it'll work. But there is something that we need to remember here, which is how to set this up really. The way you set it up is this is the Flink directory. In the Flink directory, there's a library folder. This is where you would need the jars. You need the 9, 10, 11. There's a base jar, there's 4. Then the fifth one is Kafka clients. So that's what we showed here, that you need these jars. And then when you start the shell, it will just load all these jars automatically. So when you actually start the shell like this, it already loaded the Kafka. So it knows how to connect to Kafka at this point, which is really good. And after that, the code looks very similar, as you probably have guessed, because the stream is the one which is changing. Everything else is the same. So I'll show it to you. See, the code is the same here. The stream, in the first case it was socket, second case it was file, third case the stream will be coming from Kafka. After that is the same exact behavior. What happens? So let's look at this again. The only thing that changes is how do you connect to it. So there's a bootstrap server, that's a Kafka concept, and then you start a Kafka consumer, and that's your stream. That's it. After this, you take the stream, you apply the same kind of code. You can apply any type of code. So the only real work involved is to figure this out. Like, you typically need to know the topic. This is called the topic in Kafka. This is a consumer group ID. You need to work with your admins. If you're working with a production Kafka, that is something they can help you with. And the Bootstrap servers are the actual Kafka broker systems. Again, same, you have to work with your IT organization. If you can get this set up, then it's a very easy thing. After that, there's not much really going on. As you see, I set up my own local Kafka, but the code is exactly the same. It's the same behavior. There's no difference whatsoever, right? So you see the similar kind of output. So that's how you set up Kafka. The only thing was we copied the jars, and then we need to understand how to start the Kafka consumer. That's the only thing that you require some help from your IT department. Otherwise, everything is the same.